Okay, so today we're going to talk about one of the most important topics of the whole course. We're going to try to deal with what is, in fact, sort of the central question of the course is what's the chance of a way-off sample and how can you engineer around the possibility that you're standing there holding one. Okay, so let's get to it. So what is it that you want to know? In this course, we spend the whole time working with samples, so it's easy to forget that samples are not what we're interested in. That in fact, what we're interested in is the population. The population is the group that we want information about. So, for example, suppose you're going to do a drug trial and you're going to give drugs to 100 people who have a certain condition. Well, you're not interested in those 100 people, really. I mean, they're perfectly nice people when you have ethical concerns and etc. But what you're really interested in is the entire population on Earth that has whatever condition that you're giving the drug for. So this sample you're only interested in to the extent that they can give you information about the population. The population is ultimately what is of interest. Okay, so the population is the group that we want information about. If we were to do a census, we'd observe every member of the population. But with a sample, we observe only a small subset and, of course, use that small subset to try to infer information about the population as a whole. We've seen that usually you can't attempt a census, you shouldn't attempt a census, and instead you must take a sample. And we've seen a number of reasons why you shouldn't attempt a census. But to me, the one that always sticks in my mind is the Literary Digest poll. They tried to take a census to predict who was going to win for president. They did their darndest. But because they took, instead of taking a good sample, they tried to take a census. They ended up with a bad census, and so they made a wildly wrong prediction. Okay, two examples. You make hundreds of widgets a day. I worked at a factory, for example, where they stamped out these metal pieces, and for quality testing, you take 15 of them off the line at random and you test them. So maybe you measure the diameter and you report the average diameter of those 15. Our goal is to use the 15 to get the information about the hundreds. So maybe there was a weather front came through overnight and it changes the machine in some way. This part gets longer, that part gets shorter. Is the diameter still within specs? So here's another example. We have 35 patients with a certain condition, and we're going to either give them the standard operation or the newly developed operation, and our goal is to get information about what would happen not to these 35, but instead what would happen if we gave this treatment to every person in the world who has this condition. We care about the population. We do not care about the sample. We only use the sample to infer things about the population. So despite the fact that we spend the whole time talking about the sample, don't get mistaken that we don't care about the sample, we care about the population. So what's the issue? And the issue is that samples vary. We can't take a census because almost always a census is a bad census. So instead we have to take a sample, but the engineering issue is that samples vary. Samples have a quality you have to work around. Samples vary. Suppose, for example, that you flipped a coin 100 times. Let's say you went into the chapel. You had 1,000 people. I don't know how many people the chapel sits. Suppose you had 1,000 people packed into the chapel, and every one of them took a penny out of their pocket, and every one of them flipped it 100 times. And you said, okay, everybody who's reporting 53% heads out of your 100, raise your hand. And you'd see some hands. Everybody who is reporting 46% heads out of 100, raise your hand. And you'd see some hands. There would also be some people who are reporting 50 heads out of 100. In other words, you'd see an array of different samples. You'd see a distribution of different sized sample reports, different p-hats. So we've earlier discussed the design of experiments and minimizing bias, and I don't get confused. We're not talking about bias here. Those people who took a coin out of their pocket in the chapel and flipped it didn't get a different number because they did it wrong. They just got a different number. Samples just vary. There is such a thing as bias, but there's also such a thing as routine sample-to-sample variation. And what we're concerned with today is we're worrying about what if we're standing there holding a sample that is through routine sample variation just happens to be way off. So, for example, you ask a random sample of 15 St. Michael students to rate the president 1 to 10 and you come back and report the average, X bar. So if you go out, you report an average, you go out, you report an average, you go out, you report an everybody's X bar will be a little different. Samples vary. It isn't because you did it wrong, just because samples vary. You want to know if missing breakfast affects elementary school boys more than girls. So you select some students at random. You have a control group, a treatment group. One for boys, one for girls. This kind of stuff, and you measure their scores on a math test. If I did that experiment and you did that experiment, we'd come back with slightly different X bars for the boys, slightly different X bars for the girls. Control group, treatment group. Why? Because we did it wrong? No, because samples vary. Just like the coins in the chapel, samples just vary. So what? So what? Suppose you're testing a cancer drug, trying to make it sound, very important, because it is very important. Suppose you're testing a cancer drug. After doing an experiment with a bunch of patients and running the numbers, you conclude that the drug doubles the chance that people live 5 more years. Great, wonderful. So you're going to show up at that Holiday Inn in Kansas City and you're going to report your results. Why are you walking the floor at night? So the answer goes something like this. Suppose, for example, that your sample involved, 70 patients. Just making up some numbers, but 70 patients is a reasonable number. 70 patients. You had a treatment group and control group. So in your treatment group is 35 patients. Doesn't it seem possible to you, doesn't it seem possible to me, doesn't it seem possible to you that in those 35 patients who are getting the new drug, it just so happens that 3 of them are long-lived? I mean, there are some patients who live long, there's some patients who live shorter. You just happen to get 3 of them that are long-lived. I mean, you could just happen to get 3 that are left-handed. Why couldn't you just happen to get 3 that are long-lived? So why you're walking the floor at night is because you're going to show up at that Holiday Inn in Kansas City and you did everything right. But you're going to recommend people adopt a drug that doesn't work. I mean, that's why you can walk the floor at night. So you just happened to get a sample that came out on the long live side, not because you did anything wrong, but just because samples vary. It's like you flipped a coin and happened to get 61 heads. You didn't do it wrong, you just happened to get that. So that's our concern. So the summary, I spelled summary wrong. The summary is that way offness happens. That is, when you do a study, you're standing there holding a number. You think it's probably close to the true number, but what worries you is the word probably. Is that it's possible that by happenstance you got a way off sample. Now, if somebody says to you, look, you flipped a coin 100 times, you could have got 91 heads. You'd say, no, you can't really get 91 heads out of 100. That's not really possible. But you could get 53. So that is to say, we're going to ask ourselves, what's the chance of a sample so extreme it changes our conclusion? Well, that's what we have to work out. We have to figure out the details of how you ask that question. But the central issue is, way offness is possible. You could, by accident, have gotten 3 long-lived patients. Way offness is possible. Is it realistically possible? So again, there's a common confusion here, so I want to make sure a person is straight before we leave this introduction. So with way off samples, there are 2 things that are possibly happening. Bias. We talked about bias early on in the course. There could be some systematic problem with the way you ran your study. Luck. Bad luck or good luck. If thousands of people flip a coin 100 times, some of them will get 58 heads. They just happen to get a lot of heads. If you're standing there holding one number, you're standing there holding a pea hat, how do you know you aren't one of those people? Is there a realistic chance you're one of those people? Is there a realistic chance that you got 91 heads out of 100? No. Is there a realistic chance you got 58? So we'll be concerned with, is there a realistic chance of you got a way off number just by happenstance? A lot of times in life, when you hear that a study turned out to come to the wrong conclusion, we say to ourselves, well, it must be because it was biased in such and such a way. And now that I think about it, there's a bias. Okay, sometimes there are biases. That absolutely happens. But sometimes things are way off. I can't overemphasize this. Sometimes things are way off. If something has only a 1% chance of happening, and in your career as a biomedical researcher, you run 100 studies, then in one of those studies, you got the 1% chance thing. Sometimes way offness happens. Sometimes. Okay. Okay, so to understand what's the chance of a way off sample so that we can say this is realistic possibility or not a realistic possibility, we have to understand how the samples are laid out. That is, you say, we have to understand the distribution of the samples. So here we go, sampling distribution. So I want you to imagine an experiment. You take a paper bag and you put the paper bag on the desk in front of you. You take a piece of paper and you write on it. I'm going to write a population of numbers and put the population of numbers into the paper bag and shake it up and pull them out. So I'm going to write down the numbers five. I'm going to write it down on 5 pieces of paper, shake it up, pull them out. I'm going to write the number 4 on 4 pieces of paper, 3 pieces of paper, 2 pieces of paper, 1 piece of paper. So 5 fives, 4 fours, 3 threes, 2 twos, and 1 1. I'll shake up the bag and pull out some numbers. So I'm simulating a population. Simulating taking a sample from that population. Now, StatKey has a way for us to simulate taking a sample from that population. I'm sorry, this is not quite right direction, so I'm going to show you the right directions. Let me bring up StatKey, there we go, and bring down the incorrect directions. And here I am looking at StatKey. See where it says sampling distributions? That's what we want. We're going to do understanding how X bars are distributed first, and then we're going to do understanding how P hats are distributed. So let's start in. We're going to understand how X bars are distributed. Okay, you know how StatKey works. It always comes up with some particular problem already laid out here, but we're going to enter our own. So I'm clicking on Edit Data, and I'll get rid of what they have here. Country and internet, there we go. Get rid of all that stuff, get rid of all that stuff, get rid of all that stuff, and gone. Okay, I'll click this stuff away too. And I want to have 5 fives, 4 fours, etc. Okay, so let's see. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3. 1, 2, and 1. So those are the pieces of paper in the paper bag. I'm going to reach into the paper bag and choose a sample of size 5. So I want to change this number. StatKey comes up with a 10. I want it to be a 5. 5. There we go. Okay? And now I'll ask StatKey to reach into the paper bag and pull out a sample. So here we go. Generate one sample. StatKey happened to get a sample. Can you read it? It's a little hard to read. It says 1 3, 2 4s, a 5, and I almost missed it. It's over here in the corner, a 1. So they got a 1, a 3, 2 4s, and a 5. StatKey got a 1, a 3, 2 4s, and a 5 from that one dot. Okay? So we're going to ask StatKey to try to understand what this looks like. All right, so let's reset the plot, and I'm ready to do a little more. First thing, I want to notice that it says over here, it's a little hard to read, but you can follow along on your own. It says there are 15 papers in the bag. The population consists of 15 things, pieces of paper. The average of papers in the bag is 3.667. The standard deviation is 1.291, and the median is 4. We won't be so interested in the median. So here's the paper bag. There's 1 1, 2 2s, 3 3s, 4 4s, and 5 5s. Okay, so let's, for example, take 10 samples. I'm imagining a person is reaching into the paper bag, pulling out a sample, writing down the average of papers in their samples, and then putting the papers back in the bag, shaking it up again, pulling out another handful of 5, reporting the X bar for that handful of 5, putting it back in the bag, shaking it up, like so, until they've done 10 times. So what we see, of course, is that some samples are a little lower, some samples are a little higher. Here's a sample that reports an average of X bar equals 4. Here's a sample that reports an average of X bar equals 3.8. Can you see the 3.8 over here? And here's a sample that reports 3 samples that report an average of X bar equals 3.4. So the samples are laid out in some way. It's like 10 people in the room reached into their own paper bag and pulled out 5, and we wrote down where they sit. Okay, let's get serious about this. To figure out how the samples lie, let's generate 100 samples, and now you can see it only takes place in the blink of an eye. So why not do 100? So I had StatKey generate 100, and what we're seeing here is that we're seeing something that looks a little like a bell curve. There are some samples that are pretty low. There are some samples that are pretty high, but most samples are in the middle. The true number, the absolute population, the census number, the population average is 3.667. Do you see that the average of all of these samples, there's 100 samples here, the average of all of them is 3.7. So you notice that the average of the samples is actually pretty close to the true average. So the sampling distribution is giving us some idea of how the samples sit. They're centered at 3.7 and they have a standard deviation, oh, I can hardly read it, 0.416 I happen to get. If you do this following along, you'll get a slightly different number because this all happens at random. So we got a center of 3.7 and a spreadedness of 0.416, a standard deviation of 0.416. Okay, well, let's go hog wild. Generate 1,000 samples. If you generate 1,000 samples, you see it looks awfully like a bell curve, awfully like a bell curve. And again, the middle, it says now 3.694. Remember it was 3.7 a minute ago when we did 100? 3.694? Well, 3.694 and 3.667 are looking an awful lot alike. And what's the spreadedness? 0.447. The standard deviation of this distribution is 0.447. So the computer can calculate all this stuff in a blink of an eye, so it's so easy to do, we won't have to work with actual paper bags. Okay, let's go back to the slide for just a second. There we go. So I put those papers in the bag and I entered them into Stackey. I know it's a little hard to read, but it's better to have that than nothing. Whoops, I'm in the wrong place. There we go. For this population, for this population, the census in the entire paper bag, of course, was 3.67, as we talked about up here. And the standard deviation is 1.29, but at the moment, I'm mostly interested in what happens on the next slide. Is that if I take a sample of 10 dots, I get these 10 dots here, and those 10 dots are distributed inside this graph. Some people got X bars that are close to what actually is we know to be the right number, and some people got X bars that are kind of far off. If you do 100, you get an even better picture of what's happening. Some people got X bars that are far off. Most people got X bars that are pretty close. So a sampling distribution is the distribution of the sample statistic. That is to say, in this particular experiment, the distribution of the X bars. In a minute, we're going to do the distribution of the p-hats. The standard error is the standard deviation of this distribution. So all the way up here, it says standard error. I know it's a little hard to read. Standard error equals, so that's the standard deviation of this distribution. Standard deviation of the sampling distribution has a name all of its own. You don't just call it standard deviation, you call it standard error. SE, the book often uses SE as an abbreviation. Okay, now again, if you're following along, and you should, if you're following along on Stackey yourself, then you'll find that the computer is using randomness to pick these samples. So when you try it on your own, the pictures look slightly different than mine. The numbers might differ in the second decimal place, sort of thing, but they'll be pretty close. In particular, they'll give a person a good idea of what the sampling distribution is. Think of 1,000 people in the chapel, every one of them's got a paper bag, every one of them reaches in the paper bag, pulls out 5 numbers, writes down the average, and then I stand up in front of the chapel and say, okay, who's got an X bar of 4.2? And some of those people raise their hand. That's the sampling distribution. Okay, so again, I'm concerned that on this picture, on the Stackey picture, there are a number of different boxes, and a person could get confused about where exactly we're looking. So I'm interested in this box here, the big box, and also interested in the box in the upper right, the small box. So the big box is the sampling distribution. That's the thing we're actually asking about, so that's why it's the big box. Is how do the samples lie? If you want to know what's the chance of getting a way off sample, you got to know how the samples lie. What's this smaller box up here? This is the population. This is the pieces of paper in the paper bag. So this is the population we started with and drew samples to make the X bars. This is 1,000 X bars. What's this smaller box over here? This is, if you take your mouse and hover it over a dot, it'll show you the contents of that dot. So this box down here is less interesting to us than this one here and this one here. So the distribution of the population is here. The distribution of the samples, the sampling distribution, is here. And again, you notice that the two means are basically the same. 3.667 is the distribution of the population's mean, and the distribution of the sample's mean in this particular example that I took a screenshot of was 3.662. So what's the chance of a way off sample? So let me bring up stat key again and ask, what's the chance of a way off sample? Oh, I got to find my stat key. I lost it on my computer screen. Darn this thing. Here we go. Found it again. Okay, so what's the chance of a way off sample? I'm having a little trouble with my mouse. Ah, there I go. No, there I don't go. There I go. Sorry about that. Okay, so what's the chance of way off sample? Well, for example, if I look on the chart that I have here, I notice that 2.5 is starting to get to be only a couple below 2.5. So I'll ask, what's the chance of getting less than 2.5? So I click here, do you see it says left tail? It's a little hard to read on the screen, but left tail. I clicked on left tail. And like everything in StatKey, it comes up with some default value, fair enough. So I'll click on the default value, 2.8, and change it to 2.5. 2.5. I know it's hard to read on the video, but I changed it to 2.5, and it tells you what is the number. It counted how many of the 1,000 dots are colored red now. It's a computer. It can count 1,000 dots in no time at all. How many of 1,000 dots are counted red now? 0.005. That's a half of a percent. So it thinks your chance of getting a sample this far off, getting a sample that has an X bar of 2.4, is about a half of a percent chance. If you want to know what's your chance of getting, say, a 3.0 or less, enter 3.0. 3.0. StatKey tells you that you have a 10% chance. It counted how many of these dots are colored red, and it counted the total number of dots and the total number of red dots, and it divided, and it got the 10% of the dots are red. So that's where it came up with the 10% number. Okay, hopefully I won't lose it again. So you can use StatKey to figure out what's the chance of a way off sample. It does it the hard way. I mean, it counts it, but for a computer, that's no trouble at all, of course. Okay, so we've gone through and talked about what is the distribution of samples. Well, first of all, we're interested in knowing about the population, not the sample. So if you're standing there holding a sample number, you don't say, good, I got my number. That's not right. Instead, you say, I wonder if this is an accurate number for the population. Second, we're worried about the chance of a way off sample. In order to understand what the chance of a way off sample is, you have to understand how the samples lie. Are they tightly packed? Are they way loose spread? That kind of stuff. Third, we got StatKey to draw us a sampling distribution. And then we got StatKey to count what's the chance of a sample that's this far off, or what's the chance of a sample that's that far off. So we ended up in this simulation answering the question by doing a brute force on a computer. 1,000 of these is nothing. Doing a brute force and coming to an understanding of what the samples look like. How do the samples lie? What is the sampling distribution? Okay, so we did it for mean. Now we're going to do it for proportion. So in grade school, of course, they tell you if you flip a coin 100 times, then you will get 50 heads. In middle school, they tell you that you get some number close to 50. And finally, in high school, you learn the whole story. You're likely to get a number close to 50. But there's still some chance of getting a sample that's not close to 50. In theory, you could get 85 or 91, although in practice, that doesn't ever actually happen. If you flip a coin, then the p hat is your single number estimate of the coin's true number of p. So you're standing there holding a p hat. You want to understand what is p. You don't care about p hat. You want to understand what is p. Is it possible that you flip this coin 100 times and by accident you got a way off p hat? What's the chance of such a thing? Okay, so here we are back to exactly the same situation we were a minute ago. So we have to figure out what is the distribution of sample proportions and all that. So let's go get rid of this and get StatKey back. So I'm going to go back to the front screen. Come on, come to Papa. Oh, why won't you? Oh, I don't know why you won't. Anyway, back I go. I'm going to go back to the front screen, and here I'm doing sampling distributions because I'm trying to understand how samples lie. And it says proportions, so that's where I am. Okay, I need to edit, see where it says edit proportion? So that's what I'm editing. I'm editing proportion. I'm going to flip a coin. So I want the proportion to be, don't say 50, say 0.5. Oh, I say 0.50. And we want to flip a coin 100 times. So I'm choosing a sample of size 100. Stackey comes up with a default of 200. Okay, so now I'm ready. I'm going to get here a sampling distribution of the p-hats. I'll, of course, ask Stackey to generate it for me. Just to do an example here, I'll generate 10 samples. And you see I got a bunch of different p-hats. It's as though I had 10 people in the room. Each of them took a coin out of their pocket and flipped it 100 times. It's a lot of times. One person got down there in the 46 out of 100. One person got up here in the 57 out of 100. Do you see that when you hover your mouse over the dots, they appear over here? Okay, so I'm not going to fool around here. I'm going to go straight for 1,000 samples. 1,000 samples. There was a blink there, but it happened pretty quick. There's 1,000 p-hats. It's as though I had everybody in the chapel take a coin out of their pocket, flip it 100 times, and then I said, how many people got 42 out of 100? That is, how many people are reporting a p-hat of 0.42? How many people are reporting a p-hat of 0.50? Sort of stuff. Oh, 51, forgive me, 0.51. So we're using Stackey to do exactly the same thing, only for proportions instead of for X bars. We're doing p-hats instead of X bars. So you see here, I edited the proportion to get 0.50, and I chose the sample size as 100. And I got a picture of this when I did the screenshots. I got much the same thing, slightly different. It's got a center of 0.499, awfully close to the true number, and it's got a spreadedness of 0.051. Standard error up there, it says 0.051. So we can ask, what's the chance of a way off sample? And here I happen to click on 0.62, just a click. So let's do that on the live example that I have. So 0.62, so I'm going to say right tail. Click on 0.600, because that's Stackey's default, so I'm going to do something different. 0.62. You could say 620, that's fine. And it comes up to be, it says 0070. So you can again see what happened is there's 1,000 dots. Stackey counted the number of red dots, that's all. Counted the number of red dots, divided by the total number of dots, and came up with, that's not 7%, that's 0.7%. So it's a little less than 1%. The chance of getting 62 heads or more is a little less than 1%. Not impossible, but getting awfully small. Okay? Here's an interesting experiment. I take the same screen, and I'm going to click on both left tail and right tail. I'm not going to do this live. I'm going to click on both left tail and right tail. I clicked on left tail and I made it 49%. I clicked on right tail and I made it 51%. So all that's left, all that's uncovered, is the actual bar where you're worried about the samples that somehow are right. The people who flipped a coin 100 times and got exactly 50 heads, the people who are reporting a p-hat of 0.50. And you can see from the picture in the experiment that I got the screenshot of, it turns out to be about 9.5%. In fact, in theory, this is of course going to vary from person to person. In theory, it's something like 8%. So the lesson here is that when you do an experiment, even as simple one as flipping a coin, where there's no possibility of bias, when you do an experiment, you think there's really only a very small chance that your reported number, your X bar, your p-hat, is right. Please, you didn't do anything wrong, but only about 9% of the people, 9 or 10% of the people here got an answer that is right. These other people didn't do it wrong. They just got a sample that varies, because samples vary. And your chance of being spot on is actually pretty small. So if you do an experiment and you're standing there holding an X bar or a p-hat or maybe an R, you're standing there holding an experimental statistic, you think it's probably not right. So that's the lesson. Samples vary, and your chance of getting a sample that's perfect is not very good. Instead, you think that your sample is close to the true number, but you're worried it might be far off. So we're going to have to ask ourselves, what's the chance of a sample that's far off, by understanding how the samples are distributed. Okay, so the challenge of sampling is exactly that samples vary. If you've done an experiment understanding holding a sample number, you may say, I understand that my sample number is probably not the true number, but my fear is that it'll be way off from the true number. So does that mean you can't do anything? No, 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 no. We know from everyday experience that even in the face of varying samples, you can still often make conclusions. If somebody flips a coin 100 times to get 54 heads, you just figure that probably their coin is good. Probably the true number is 0.50, but their 54 is a little different. If instead they got 87 heads, then you'd say that's awfully far from 0.50. I think something might be happening here. So even though samples vary, sometimes the evidence is strong enough for us to be confident about the conclusions that we make. Okay, so the lesson for today is, please, samples vary. We're concerned about the possibility of a way off sample, but by understanding how samples vary, we can hope to see that there is only a very small chance of a way off sample, and we can speak with considerable confidence about our conclusions. Okay, very good. Now next time we'll talk about making those conclusions. So a very important section today, because we will be doing exactly this concern for the rest of the semester. Okay, very good.